phi star is the eigenvector for matrix P corresponding to eigenvalue lambda equal 1. Because this means pi star times lambda on the other side is pi star times P. Vectors who have such a property for a matrix are called eigenvectors. Geometrically, what this means, if you look at the vector pi star in geometry, it means when you multiply with the matrix, you don't change its direction. Because this, lambda is a scalar. So this says, multiply with a scalar, you keep the same vector, but you can make it longer or shorter, but the same direction. This says multiply with the matrix. Multiplying with the matrix usually changes the direction of the vector. The special vectors for which multiplying with the matrix does not change the direction, they're still on the same line, are called eigenvectors for that matrix. And any mathematical infrastructure program like MATLAB will have a specialized function to get you the eigenvectors. The many eigenvectors, the one that you want is the one for lambda equal 1. Right? So this means P does not change direction of pi star. So that's not for our lecture or material. Saying for people who do math and do linear algebra, instead of solve a linear system of equations, they could just ask MATLAB, give me the eigenvectors of matrix P, get the one that has the eigenvalue equal 1. And that's the vector we're looking for. So, attendance sheet. Let's start from here this time. Where are we? We are at algorithms, right, for sorting and searching. So what did we say? I think we were talking about merge sort. So merge sort of I have this array, so say A. What it does, it's a procedure. So sometimes we write it like a kind of set of rules that we need to steps to solve this problem. So what this does, it calls itself for the first half. Let's say A to the middle. And then it calls itself for the other half, middle plus 1 to the end. So the middle of an array is roughly 1 plus n divided by 2. Take the floor of it. And then it's merging the array of 1 to middle and the 1 to middle plus 1 to the end. So how does that look like? If I start with, this is example we did last time, 63, 7, 2, 4, 8, 1, 5. This is my array. And in an array, we always write inside the array the values. If we write indices or position, it's 1, 2, 3, 4, so on and so forth. What merge sort does, it does a split. This is the split part, and this is the merge part. Kind of like divide and conquer type of problem. So I split in half. I say, that's my left side. This is left, this is right. Or in my notation, this is A from 1 to the middle. And this is the other half, A, this is the whole array A from middle plus 1 to the end. So I split in half. And then the philosophy of merge sort is that I want to sort first this part. So that's why it's calling itself. That's a recursive call. Both of those. It calls itself. So it says, okay, how can I sort this thing? So what's happening next is it's splitting again in half, right? So 6, 3, 7, 2, it's now split in half. This is the main split. Then 4, 8, it's splitting again in half. Let's say this is a split. 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 And then it's splitting further. Now it's going to call merge sort. So I call already merge sort here. You can say that's call 1 in here. Now I'm calling call 2. I'm going to do 6, 3, 7, 2, 4, 8, 1, 5. So that's 4 splits now. Split, 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 split. And now when I'm on this size, I can sort those because it's very small. So I get 3, 6, 2, 7, 4, 8, and 1, 5. Once the merge sort returns, what those are sorted, now I have to do a merge in here. So when I merge these two, I get 2, 3, 6, 7. And I merge these two, I get 1, 4, 5, 8. And then when I merge the last merge, so from 2, 3, 6, 7, I merged with 1, 4, 5, 8. So once I sort the halves, I'm now merging the sorted halves. Merging sorted things, it's easy. How do I merge things that are already sorted? Yes?
Keep the first part, like the first half, and move the pieces of the second half into the right spot.
That's conceptually, but in practice I do it differently.
You look at the first indices.
I start with the first and first, and I say which one's smaller. Between 1 and 2, I choose 1, and then I advance. Let's say I start with a P and a Q here, 2 pointers, so, or indices. Advance which one? If I choose the 1, I have to advance Q. So now Q, it's A of Q is now 4. A of P here is 2, and A of Q here is 1. I compare 1 and 2. Now I compare again A of P. So I'm comparing A of P versus A of Q all the time. And now I have 2 from here. So that was 2 versus 1. Now I have 2. P didn't move. It's still at 2. Versus who? Q moved. Q is at 4. I choose the 2 and advance P. Now A of P is now who? If I move the P. You guys following me? I start with P in this position, Q in this position. Those are indices. So P and Q are indices. So I compare 2 and 1 the values, A of P with A of Q, and I got this A of Q is smaller, I write that down, and I advance this index Q now. Then again, I compare A of P with A of Q, I get 2 versus 4 now, because Q has advanced to 4. I compare them, I get the 2. And I advance P. Now A of P is, who is A of P now if I advance P? 3. The next comparison will be 3 versus 4. 3 wins and advance P again. So A of P is now who? 6. Then I have 6 versus 4. 4 wins. Advance Q. So A of Q is now 5. So then I'm going to get 5. Then the 6, 7, 3, 8. So if you look at this is a sorted. So I have 2 sorted arrays. I start from the top of both of them, and I always compare to see which one is the next element that's coming, and I advance the pointer in that one. That's the merging procedure. So I can merge things and get the array sorted. And we said, what's the running time? We care about asymptote. In all running times, we want the order. So we don't care about the exact running time. So let's say T of n is the runtime for array of size n. Of course, the runtime will depend on how big the array is. What is this procedure telling me if I'm the computer running time? The running time for n is I have to do merge sort for a half. That is T of n by 2. That is the left side. Plus another T of n by 2. That is the right side. Plus how fast is this merging procedure that I just described here? If I start with P and Q, take the minimum, advance, so on and so forth. How many operations is going to take this procedure here? Yes.
And
That's linear. So the order is about n. I say order for now informally. Please accept that for another week. Next week we'll define formally what order means. But for now we just say something's linear is like n times something. Quadratic is like n squared times something. Logarithmic is like log of n times something, right? And formally we'll decide what that is later on. So this is linear because it only goes through everything once, right? Once it decides what to do with this 3, it moves away from 3. So at each step it moves either P or Q. There's only so many steps to advance in here. 8 in this case, so it's going to be linear. Merging procedure is linear. So this is linear. So this is something like n steps, or n times a constant. Maybe it's not n, it's 2n, who knows, because I have another condition. But it's something like linear. So everybody understands where this is coming from? I want the merge sort running time for n things. That means running a merge sort for half of the things, a merge sort for the other half of the things. Whatever this function is, t, which I don't know, it's going to have to be half plus linear. Right? Because that's how the procedure goes. This is a recurrence. We don't want the exact function t of n. We want the order. So we don't care if it's 3n plus 5 or 7n squared plus 4 or something like that. We care about the order. Is it like linear, or is it like quadratic, or is it like logarithmic? Which kind is it? So we're going to study recurrences. Not today, but today we're going to solve this recurrence. So the way to solve that recurrence T of n is T2 n by 2 plus n. I'm just going to say n from linear to simplify it. This has to be for every n. Bigger than something, right? This is not just for one n. That has to be true for any n. N equals 8, n equals 20, n equals 100. So I'm going to insist in running this recurrence, like iteratively. So if I apply the recurrence again to T of n by 2, what would I get if I replace this n here with T of n by 2? So I'm going to write the 2 is the 2. The T of n by 2 becomes something because I'm going to apply the recurrence now. What's the recurrence in T of n by 2? So I'm going to apply the same thing, but not for argument n. I'm going to apply it for argument n by 2. What do I get?
T of n by 4?
No, I don't get 2 T of n by 4.
Oh, yeah.
There's a 2 in here, right? So
Yeah.
2 T of n by 4 plus, who's this n now? N by 2, right? So I'm just applying that recurrence again, and I still have a plus n here from before. This in here is just the T of n by 2, this whole parenthesis. The 2 is in here, and the n is in here. So this is what? If I write it nice, this is 4 T n by 4 plus 2n, let's say 3n, right? Because 2n, what did I do? That's, I don't have enough n's here. 2n, right? And now I can apply the recurrence again. 4 is the 4. Who is T of n by 4? If I apply the recurrence on argument n by 4, what do I get? 2 n by 8, right? Plus what? N by 4 plus 2n. So now how many, the coefficient in front is going to be 8 T of n by 8 plus how many n's I get total? Let's apply it again. 8. Now who's this? 2T of n by 16 plus n by 8 plus 3n. So I get 16 T of n by 16 plus how many n's? 4 n's, right? So I can keep doing this. How many people follow me here? I can apply the recurrence on any argument I want. And anybody sees a general pattern, suppose I apply recurrence k times. After, this is after 1 time, after 2 times, after 3 times iterations. So that's, we call this k iterations. What do I get? Who can guess who the coefficient in the front is going to be?
2.
This 16 will be what? To the k, T of n by 2 to the k, right? Because every time I apply it, I get from 2 to 4, from 4 to 8, from 8 to 16, right? So if I apply k times, it's going to be 2 to the k. Plus the free term is going to be what?
Isn't it k plus 1?
Right. K minus 1 iteration then.
Okay.
K is a generic counter. We care about the shape. What's going to be this 4, this 3, 2, 3, 4? What's the relationship between this coefficient and the power in here? If this is 2 to the what? And this is a 4. This is 2 to the 3. So that's K. That's the general form. It's still a recurrence because it has a t in it. I didn't solve it, right? It's still defined on itself. A recurrence means I'm defining a function on itself. But now we can say, okay, we want what k should be? How far do I need to go with this thing? When do I stop?
1 base 2 of the length of the array.
What? How much can I go? What's going to stop me to go forever in here?
You get to it.
Suppose I start with an n that's 1,000,000. How many times can I do this? At what point, what forces me to stop this iteration procedure? Yes,
When the list now has like one element, you can't split it up.
which
That's
is the
gonna
list,
stop
where's
it.
the list in here?
N. When n is 1.
You
Or less.
mean this n? This is not the original n? That's 1,000,000.
Oh, when n over
N over 2 to the k
less
is
than
the size of the problem now,
Yeah.
right? So this here is the size of array or list, whatever I'm doing. I'm doing arrays, by the way. Arrays are different than lists, right? So we want n to the 2 to the k to be approximately 1. That is when I stop, because if this is 1, that's t of 1, I can't split in halves anymore. Right? So that means, by the way, what k is approximately give me n by 2 to the k is 1? Yes,
Log base 2 of n.
about log base 2 of n. About. I say approximative. Right? Maybe the rounding or the ceiling or the floor, right? What k do I need? Log base 2 of n, because if I plug in the log, n divided by this is going to be n by n is going to be roughly 1, right? So what do I get? I get 2 at log base 2 of n, t of 1. That was my whole point of figuring out that k, to get inside 2 of 1, plus log 2 of n times n. Right? So I replace k here. I say, what's the end k by doing this? N k is about logarithm of n. So 2 at log n, t of 1 plus n log n. So now how much is 2 at log base 2 of n? That's n. This is a constant, t of 1. I don't know what t of 1 is, but it's some constant value. It's a fixed value. Plus n log base 2 of n. So this is linear here. This is not linear. This is the order n log n. And when we have two terms in an expression, the bigger one dictates the order. Like if you have an n squared and an n, the n squared dictates the order. The order of this is going to be n log n. When you get two things, one is bigger than the other, the bigger one always dictates what happens to the whole expression. So the order is going to be n log n. That is merge sort. We're going to solve a lot more recurrences very soon. And when we do recurrences in computer science, we care about the order. So there might be a constant here that's a 2 times that or 3 times that. We don't care about that. We care it's roughly like n log n. I want to go back a little bit to insertion sort. We did that before, insertion sort. And we say, how does that go? So the array, I'm going to use the same array, 6, 3, 7, 2, 4, 8, 1, 5. You don't have to write it again because it's what you wrote last time. The way that went was saying, start with a 6. So that's my output. 6 da da da, starting here. And then when the 3 comes in, new value equal 3, I have to figure out, initially, I put the 3 right next to it, but then I have to move it to a bunch of steps. I have to flip it, remember? Was 3 before 6? And then the new value I'm reading is a 7. I start now with 3, 6, 7. This is good, doesn't have to move. Every time I'm reading a new value from my array, so the new value is going to be 2 now. I'm just putting it at the end. 3, 6, 7, 2. But then I have to move it. I have to take these 2, right, and swap it. So the steps were like 3, 6, 2, 7. And then that's a swap. Then I have to do another swap because 2 is still not in the right spot. 3, 2, 6, 7. And finally, I'm going to get 2, 3, 6, 7. Now that I have this array, I get a new value, 4. And then I get 2, 3, 6, 7, 4. And then again, I have to swap 4 2 times to get it into the right spot, which is 2, 3, 4, 6, 7. So on and so forth. Guys, remember insertion sort from last time? I add the value at the end, and then I move it to the left side until it gets to the right spot. Some values don't have to go at all. This 7 is already in the right spot. But this 2 has to move all the way to the front. That is 3 spots. This 4 has to move 2 spots. So on and so forth. So what's the difficulty here? The runtime is, say, worst case, is the first one has to do no move, right? The first 6 doesn't swap at all. I just put it there, the first one. But this value might swap in the worst case, 1 position, right? The second value might swap 2 positions. The third value, all the way to n minus 1. Okay? So that is, if I'm really unlucky, this value swap once, this value swap twice, 3 times, 4 times. Everything has to swap all the way to the end. So worst case for this is sorted backwards. If it's sorted backwards, every value has to swap all the way to the front of the array. And this would be n times n minus 1 by 2. That is quadratic. The order is n squared. It's not exactly n squared, but again, we care about the order, not the coefficient of it is n squared. Even though it's 1/2 of n squared, still n squared. So I've said all that last time, I know. So somebody, Jimmy, says, you know what I'm going to do? Instead of using an array of the output, I'm going to use a list. So here's the deal with this array. Why do I have to swap so many times? Remember binary search? What was binary search? It was saying, if I'm looking for a spot to put something, I can find it much faster than linear, right? That's what effectively we are doing with this 4, right? Aren't we looking for the right spot to put a 4? Isn't this already sorted? Didn't we learn that binary search will be a faster way to do it than linear search? This going 1 by 1 positions to the spot is a linear search effectively, right? I'm swapping once, twice, 3 times, whatever, until I get into the right spot. But since this is already sorted, wouldn't that be faster to find the right spot with binary search? So here's an idea. Do insertion sort, but find the right insertion spot with binary search. So what I mean here to say is when I have this prefix 2, 3, 6, 7, and I'm adding the 4, instead of swapping it one by one, I'll say find position, the right position with binary search. That position is P number 3, right? The right spot for this guy is in position number 3. And then insert it. Wouldn't that be faster? How long is going to take me, on average, to do linear search to find the right spot? It's going to be linear, right? It's going to be roughly, if there are 4 things here, it's going to be roughly 4 by 2 on average. But if I do it with binary search, that's going to only take log n steps, right? How many people remember binary search from last time? Good. Why is this still not working? Yes?
Because you can't insert a piece into a part of an array.
Even if I find a position in log n time, that's going to be log, if this is k currently, that's about log base 2 of k steps. I know binary search will only take logarithm time to find the spot. What he's saying, I think, is like, how do you insert it in an array? You got to move the other guys. So moving the other guys, inserted implies move half of the array. That means still linear in k, right? Because if this is k, I still have to move k by 2 positions of the array to make space for the 4. I absolutely need everybody to understand this phenomena. I can find the spot of the 4 with binary search quickly, but I cannot insert it, because inserting means moving half of the array, and moving half of the array will take k by 2 steps. So it doesn't help me to do the binary search, because the moving part is going to kill me. It's still linear. How many people with me? Right? Okay, here's another idea. Idea 2. Use a list for output. Not an array. Now I'm going to make a clear distinction between a list and array. Conceptually, there is one. Python might call it lists, or Perl, that's actually an array. But in a list, the values are like this. 2, there's a pointer to 3, there's a pointer to 6, and there's a pointer to 7, and there's a pointer to null. That tells me the list ended, and that's the head. You guys seen linked lists before? How many people seen linked lists? So the order to traverse a linked list is to start from the head, go to whatever you need, so on and so forth. Insertion in a list, it's easy, right? If I tell you insert something after 3, how would you do it? Do you have to move anything? Why not? Somebody else. How do I insert in a list? If I tell you that that's a memory address, right? I tell you here's the 3. How do I insert something between 3 and 6? Yes.
Have, say, between 3 and 6, you would then have 3 point to the memory address of the thing you're adding, and then have the thing you're adding point to the memory address of 6.
Very good. So insert, I just create that object in memory 4. I break this pointer, and I say now 3 points to 4, 4 points to 6. These objects in memory are exactly where they were before. I didn't move anything. I created a new object, and I changed the pointers, the way this in memory is just in the same spot. This in memory is in the same spot, same. I added a new object 4, a number or whatever, and I created different links. So insertion is a constant time operation. Will this work now? So can I do binary search to find the spot, and then insertion immediately in the spot? If I use a list, can I do that? sure?
Are there like limitations to binary searching in the linked list because of the way it's constructed?
Not just limitation, binary search doesn't work on lists. Right? It doesn't work because in a list, how do you do binary search? Now those are objects in memory that have links between them. There is no index 1, 2, 3, 4. It's just an object with a value, that's the 2, a memory pointer to another object. How do you do binary search? What's the first step in binary search? How can you split the list in half? You don't know where the middle is. The only way to get to the middle would be to actually traverse the list to the middle. Because the way to work with lists is to start from the head and move so many things. So the problem with the list is that binary search does not work. Can I do it binary search, keep an array and a list? Do the binary search in the array and the insertion in the list. Would that work? Why not?
Because even though you be able to binary search to get an index in the array, you still don't have an index to use for the linked list because the list doesn't use indexes.
Yeah, but I know where to split it now, maybe. I don't think that would work because then I have to still update the array for the next round. Even if I could do that, how do I get this array to work for my next round? How do I still have to put the 4 back in somehow? What do we do here? So we can do binary search to find the right insertion spot. That should be some clear idea that that is the right thing because this is sorted. When you see something sorted and you're looking for a spot in it, that smells like binary search miles away. All right? And then insertion shouldn't be that hard if I'm not using an array. So is there something between a list and array that I could somehow do both?
Can you use a binary tree?
That's the one. How about insertion sort with the binary tree? How about we try both steps? So we want find the spot in log k time and insert new value also log of 2k time. I don't need it to be constant like the list because if I spend so many units to already do the finding, I can spend the same units to do the insertion. So let's do a tree based on that thing. The first is 6, right? That's the root. Now I get the next value 3. How do I insert 3 into the tree? There's a property that binary search trees must have to be valid, which is what? Somebody else.
If it's less than 6, you put it on the left side.
Left side, right? So 3 is less than 6, so 3 goes on the left side. So 3 is less than 6, that means left. Right? That's how insertion goes. What's the next value? 7. 7 is greater, so 7 is greater than 6, that means right. So here's the 7. What's the next value? 2. Well, I have to start from the top, so what do I do with 2? 2 is smaller than 6, so where do I go?
Left.
Left. And now I'm here, what do I do? Left again. So this is 2 smaller than 6, and then 2 smaller than 3, so 2 gets here. What's the next value? 4. Where's 4 go? How is 4 compared to 6? Small, and then bigger, so that means goes on the right side. So small first, 4 smaller than 6, but then more bigger than 3. Next value is 8. 8 is how compared to 6? Bigger again, right? So first 8 is bigger than 6, and then 8 is bigger than 7. And the last value, 1. 6, 3, 2, 1 goes in here, right? Smaller, smaller, smaller. How about the 5? It's smaller than 6, but bigger than 3. This is the computer science bedrock, binary search trees.
On
If you make a binary search tree of an already sorted list, don't you essentially just get a linked list?
Yeah, I'm getting there. Just wait 2 minutes. Right. He's right. He's right. What's up with those trees? Sometimes work, sometimes they don't, and that's the case where it doesn't. But do everybody understands the binary search tree? It has to have a fundamental property. That is, every value you have, let's write this fundamental property here. Binary search tree. The property is every time we have a value and we're going to write a whole subtree here, we call it left, and a whole subtree on the side can be bigger, we call it right. This is not just one element, it's the whole, everything on the left side. Everything on left must be smaller than the value, must be smaller than everything on the right. So that's not true only for the root. Even if you pick this node as the value, 3, everything on the left side of 3 has to be smaller than 3, and everything on the right side of 3 has to be bigger than 3. That's the property of a binary search tree. And it's not true just for the immediate children, 2 and 4. It has to be true for the entire subtree. Yes? Yes?
If you had another 6, where would it go in the tree?
Right. So how about we apply the procedure? We have another 6. 6 than 6, it's equal, so we can go either way, right? Let's say we go right. How about here? This would be the other 6. If we get another 6 and say initially we go left, 6, 6, 6, another 6 will be here. Yes?
If there was a bunch of 6s, you'd have to do it the same way every time, right?
Or randomly. Notice that this tree still satisfies this relation. Every value has lower left side and bigger right side. So if I look at, for example, this subtree here, how is this compared to 3? All these values here, how are they compared to 3? Greater. But how are all those values compared to the 6? Why? Because the first step was to the left, so all this subtree must be bigger than 3 but smaller than the 6. Now we understand binary search tree construction?
Yes.
Hands up. Very good. Remember, this is an absolute bedrock. You'll hear it in every single course you take. Okay? Every single course you take is going to have some binary search tree in it. Now, did I achieve find the spot in locate time? How fast does it take to find that spot? That's up to Daniel's question. Is it true that finding the spot will take about log k positions? And is it true that when insert a new value, it's going to take locate time? Well, that's the same. The moment you find the spot, you insert the value. So that's easy, the second one, right? It's actually going to take only one operation, not locate, because once I found the spot, I can just insert it in that spot. Right? But how about this locate time? So for a binary search tree, this is true if tree is balanced. Balance means the branches are not disproportionate. I think that was Daniel's question. What about a tree that is not so good looking? For example, what happens if I insert not a sorted array? I could do this with a sorted array, but suppose I do the following: 2, 1, 4, 3, 6, 5, 8, 7, 10, 9, 12, 11. How does this look? I start at 2. Where does 1 go? Left. Where the 4 goes? How about the 3? First,
Right.
right, then left, right? So I get a 3 here. How about the 6?
Right, right.
How about the 5? Right, right.
Left.
How about the 8?
Right.
7 goes here, right? How about the 10? You can see how this goes. This is not a balanced tree. I'm gonna drag a little bit more here. This is what? 12, and then the 11 is gonna be here, right? The problem with this tree is that it's not balanced. How big is every branch to the left? 1. How big is this branch to the right? After 100 operations, how long will this branch be? This path from here to here, if I insert 100 numbers in this order, how big is that branch gonna go?
50 or something.
About 50, right? 50 is not log of 100. This branch here, which is unbalanced, this branch is about n by 2 size. For a balanced tree, I need every path, root to leaf to be about log n. Every path has to be roughly logarithmic. This is not logarithmic. Right? So what makes a tree balanced? Every single path, it's about logarithm or less. What makes the tree unbalanced? This is unbalanced. There is a path that's about linear. Right? I only need one path to screw up my tree.
So if most trees aren't perfectly established, like even the one we did wasn't perfect, but that's so close enough.
So that's not an easy question to answer. Like on average, are the trees always balanced on average? Depends what average means.
When do we know? Like where is it too unbalanced for it to round for?
So we need some sort of condition to detect unbalance. Most important thing, we need a fix. So once you get to the master level, which is not in this class, you're gonna see something that says if the tree becomes unbalanced, fix it. And that's become a red-black tree. So a red-black tree is a binary search tree that's always balanced. Because if it gets out of balance, I'm fixing it. I take this whole subtree that's unbalanced and I move it around and I still have a binary search tree, but I ensure all the time that that's balanced. Because if it's balanced, I can do these operations fast.
Could you rebalance it by shifting the root? So
I can rebalance it by shifting the root, but that's not how rebalancing goes. Usually it's by taking this 7, for example, and move the 7 in here and the 8 on the other side. The rebalance is sub 3 by sub 3. That's not even, I don't think you're going to study it even as an undergraduate. I think it goes to the master level material. How do you do this systematically? Balance the trees. Remember, if you have a binary search tree, it's an amazingly efficient structure if it's balanced. If it's not balanced, it ends up being a list, effectively. Because it's this one path that's one after the other, and just a long list. That answer the question? So when you do this, you want to make sure every once in a while that you balance in your tree. So that is proper insertion sort with a tree that will achieve, in principle, still n log n time. Because if I keep the tree balanced, log operations for each object times n objects, I get so if it's balanced, that implies n log n time total. But only if it's balanced. One more procedure for sorting. Here's another idea, similar to merge sort. I'm going to take the same array that I had before, 6, 3, 7, 2, 4, 8, 1, 5. What is merge sort doing first? What's the first step in merge sort? Yes. Split it in half, right? Well, we're going to do a split, but not in half. So this procedure does a split, but not in half. What it does is say split by a pivot value from array. This value is from the array at random. So I'm going to assume the value that I'm picking here, the first value is 4, that one. And what it does, it says, okay, 4 is here, it's fixed now. This split does the following. It moves values smaller than 4 to left and values bigger than 4 to the right. But not sorted. So 6, is 6 bigger than 4 or smaller than 4? So goes to where? To the right, right? Right here. How about 3? Is 3 smaller than 4 or bigger than 4? Goes to the left, right? How about 7? Here. How about 2? Goes here, right? It doesn't have to be sorted. So I can put the 2 here or I can put the 2 here. Remember, this doesn't have to be sorted. Just have to be on the right side of 4. 4 is some value I picked initially. What's the next one? 4 is 4, that's itself. How about the 8? Maybe the 8 will go somewhere. Again, it doesn't mean to be sorted, the right and left side. We'll throw it in just like you throw something in a bag. But make sure it's the right bag, either left or right. 1 goes in here, right? 5 goes in here. That is the split. So let's recap what the split does. Picks a value, 4, fixes the 4, and then says, look through the array. Everything that's smaller than 4 will go to the left. Everything that's bigger than 4 will go to the right. And now that's my array now. What did I achieve? Did I sort anything? Is it sorted? No. But what did I achieve for sure? What do I know about this 4 now?
It's in the right spot.
This is in the right spot. And because this is always smaller, this is smaller than the 4 and this is bigger than the 4, it means now I can just sort this part, right? If I sort this part and then this part, wouldn't I get the whole thing sorted? Would I have to interleave between the parts? No. So now separately, sort the left side and right side. Separately, I mean independent. I can do it in parallel, right? I can start this sorts now. I can start it on 2 computers. I can send the left side to one computer and the right side to another computer and say, sort it for me. They don't have to talk to each other because those are independent now to each other, right? Or I can sort it sequentially. I can say, sort the left side first. When you're done, sort the right side first. Right? So how do I do this? How would I sort now, say, the right side? 4 is here. What's going to happen on the right side? How do I sort the right side? Yes.
Pick another big value.
Repeat, right? Pick a value. Say I pick the value 6. I have my 6 now. What's going to happen with this? 8 is going to go where? Right side. 7 is going to go right side. 5 is going to go left side. Now this is in the right spot. Repeat in here. repeat in here. And by doing this all the way to small arrays, I sort everything. How many people follow me? Good. Is this procedure has a name? Yes.
It's quick sort.
Quick sort. Quick sort needs the following tricky thing. It's easy, very easy to understand. So what quick sort does, quick sort of an array A, it first does the split A by value B. So now after the split, I'm going to have V is in the right spot here. This is smaller than V, and this is bigger than V. And then apply quick sort on the left side. So let's say that's the left and that's the right. This will have to be defined formally for you guys in the algorithms course. Like how do you actually manage the whole thing? That is quick sort. Is it a recursive call? Definitely recursive calls. It has a worst case which is very rare. Order is going to be n squared. Average case, which is very often, the order is going to be n log n. But there is a fundamental property. Let's call it condition, necessary condition. The split function has to work in linear time. The order has to be roughly the size. I won't give you the recursion of quicksort because it's a little bit too advanced for us. It won't be advanced after Thanksgiving, so we'll put that recurrence. There's a recurrence because it's a recursive procedure. The running time is going to be a recurrence. And it is true that the worst case of quicksort can be n squared. You can find an example where doing quicksort, by picking those random values, being unlucky all the time, you can get n squared. What unlucky would be when I pick this random value 4? What's unlucky? What would be an unlucky pick? In an extreme. Either too big or too small because it doesn't split anything. What would be a lucky value? Somewhere in the middle. It turns out if you pick them at random, it's virtually impossible to be unlucky all the time. So the worst case requires to be unlucky all the time. Never going to happen if the array is big enough. So people use quicksort in practice all the time, even though the worst case, it's worse than merge sort. Merge sort is guaranteed to be n log n all the time, but quicksort is easier to implement. And quicksort on n at least 20 is virtually impossible to be unlucky for all splits. But we need this condition that's going to take some algorithmic for you guys, algorithms to figure out how to make it work. The split has to happen linear time. So once I pick the 4, I have to be able to do this. Put the smaller values here, bigger values here, with one traversal of the array. Right? So what I'm doing here, I'm only looking at all elements once, that's why it's linear, and decide smaller to the left, bigger to the right. Easy to say. You can see why I only need to traverse the array once. But how do you actually move objects in an array to make it work in linear time? Well, we had the same problem here. I could say, binary search works in log n time, right? And insertion works in constant time in a list, but engineering-wise, not too easy to make it work. You need a tree to make that happen. And the tree has to be balanced every once in a while. Same thing in here. I could say, just traverse the array once, the smaller values go to the left, bigger values go to the right. That's linear, because I only go once for each element. But to actually make it work, which is possible, you need to program it correctly. So many algorithms book will have a function called partition that will do the split in linear time. And that's essential. If the split doesn't happen linear time, the whole thing falls apart. That is what to have to say about sorting. Quicksort is another thing for now, so we're going to keep talking about it, but I don't think you're going to have it in the exams and homeworks. I want to move on to how do we solve these recurrences and these formulas and all of that. So, how do we do sequences as numerical and their series, which is a sum of a sequence? For example, how about this sequence here? This is going to come, it looks like a new thing for now, but what it really does, it solves these recurrences. Once you run an algorithm and you have a runtime, it figures out, okay, how do you compute the runtime from a recurrence? You're going to need this kind of math background to do it. So there's an algorithmic computer science part, but then there is the math you need to figure out this runtime. So 4, 7, 10, 13, 16, which one do you think is the next guy here? 19, right? So this series have the shape, this is A times X plus B, or X is the index. So who's A in here to get this series? Let me put in here, series. So what X is X in here? If I want X to be 1, 2, 3, 4, 5, 6, what A do I need and what B do I need to make that happen? Is 3X plus 1. Okay. If I look at indexes 1, 2, 3, 4, 5, 6, and I do A equal 3, that's A, and that's B, I get that. How about 40, 70, 10, 13, 16, and 19? What is that? The index is the same, 1 to 6. What is A now? 10 times X plus? No? How do I get 40, 70? Well, that's 100, right? Sorry, my bad. So it's 10x plus what?
Yeah.
30x plus 10.
30x. Sorry about that. Sometimes we wonder with the instructors, not the TAs, the instructors, if we take the quiz, how well would we do? You know?
I think that too.
It's a fair thing to take the quiz and see how well we do. So this stuff has a name. How do we call this kind of thing? This is an arithmetic progression. How about the next one? more arithmetic progressions. -7, -1, 5, 11, 17, 23. What is this? So again, I have indexes 1, 2, 3, 4, 5, 6. What is this? The difference between them has to be the A, right? The difference between those things is 30. That's the A. The difference between them is 6. So this gotta be 6x. Right? See the difference? 6, 6, 6, 6. The difference in here is already 30. Right? That's what characterizes this arithmetic progression. I'm going to need more space, so I'm going to put this one on the other side. The difference is constant. The delta difference. What's the difference in here between them? 3, 3, 3, 3, 3. That's why A came up 3. So in here it's going to be 6x minus 13. The delta here is 6, the A. Here's another type of sequence. 1, 1/2, 1/4, 1/8, 1 to the k, so on and so forth. This is different. This is not an arithmetic progression. This is a geometric progression. So in here we don't look for differences. The difference between those is not constant, right? Like in here. What is constant in this kind of? I'm going to put another one just to give you an idea. 3, 6, 12, 24, 48. What's up with these progressions or sequences?
The ratio is constant?
Ratio. Ratio is 1/2, right? The ratio between them, again, 1/2. The ratio here is 2. Ratio 2. 2. So geometric progression looks like some constant times x to a power r. This is, instead of a and b, now we have a constant times x to the power. So what is this one here? X again is 1, 2, 3, 4, 5. That's the x's, the indexes. How do I write this as? Who's the r? The ratio? R is the ratio, right? So this gotta be x at the power 1/2. Sorry. You got too far ahead. The index is the power, so r to the x. So how do I get this stuff? It's 1/2 at x. What do I need to put in front of it? What is this c? So the r in here is gotta be 1/2. What is the c? 1. Well, for x equal 1, what would I get? 1/2 by my first one is 1. So how do I fix this?
X minus 1.
Let's say I want to keep the index 1, 2, 3, 4, 5. Can I fix it from the constant in the front? How do I do that? That's a 2. What is this one here? What's the ratio? 2, so it has to be 2 at x. But it starts with 3. So what's the constant in the front of it?
3 halves.
3 by 2?
Sorry.
Will that work? That's the constant. How about 300, 600, 1200, 2400, 4800? The ratio is what? Is it a constant ratio? Ratio is like before, it's 2. So this is going to be 2 to the x times what constant in the front?
300.
Over 2.
150 maybe. But first x is 1. I get a 2 here. I need to multiply with 150. How many people follow me? Arithmetic progressions, geometric progressions? Let's try another thing here. I have another one that's neither arithmetic nor geometric. Is 1, 3, 6, 10, 15, 21. What is this? Is that a constant difference between them? What's the difference here?
2, 3, 4, 5.
What's the ratio? Is the ratio a constant ratio between this and this is? 2. The ratio between this and this? It's clearly neither arithmetic nor geometric. So the difference is constant here. In here the ratio is constant. In here the difference is, if I compute as 2 between those, and then the difference is 3, 4, 5, and 6, right? Now the difference of the difference is what? So I got first the differences like I get in an arithmetic progression. Now I'm getting the differences of that array. What do I get? Okay, so this is called quadratic sequence, and the difference of the difference is constant. And how do we write this? This is something like ax squared plus bx plus c. So instead of being ax plus b, which is a linear function, or degree 1, this is a quadratic function, or polynomial of degree 2. So who's A and who's B and who's C to make this work? Anybody can tell me?
3 halves, 1.
Let's see, 1/2 x squared plus
3 halves. Plus 1.
3 halves?
3 halves. 2 minus 1 half.
Not sure that's correct. I got the one.
I started at 0. Sorry.
No, the first index is 1. So that's.
Then you can plug in x minus 1.
So I've got here for the C I got 0.
Okay.
And for this I've got x by 2. Would that check out?
Yeah.
So let's check for this is 1, 2, 3. This is the x, right? The index. 1, 2, 3, 4, 5, 6. How much is this value for 3? That's the same as x times x plus 1 divided by 2, right? So let's check it for 3. This is a 4 here. 3 times 4 by 2 is what value? I'm checking my hypothesis here for 3. What do I get? 3 times 4 by 2 is 6, right? How about for 5? 5 times 6 by 2, will I get 15? How about for 6? 6 times 7 by 2, do I get 21? How about for 1? 1 times 2 by 2, do I get 1? So you have to figure out, if somebody shows you a sequence like that, you figure out, okay, the differences form an arithmetic progression, therefore, that's a quadratic thing. But how do you find A, B, and C?
Yes, check.
You can solve some equations. A, you can say A times 1 squared plus B times 1 plus C has to be 1. Then A times 2 squared plus B times 2 plus C has to be 3. And A times 3 squared plus B times 3 plus C has to be what? 6, for example. I can solve those 3 equations. Or I can first figure out what the arithmetic progression is by x plus b, and figure out from there how to make a quadratic progression out of it. Right? Yes?
You can do that with combination. Right? You do 1 times x choose 0. So if you're starting at 1, then you do 1 times x minus 1 choose 0 plus 2 times x minus 1 choose 1 plus 1 times x minus 2 choose.
I'm not sure the choose, I think
Sorry,
the
choose 0 each.
the coefficients, binomial coefficients appear here because I choose that progression, but I don't think they appear all the time. Not in any progression you get that.
In the arithmetic progression. Or in the quadratic.
This is a quadratic progression.
But for your differences, you do your differences.
Right, so I could solve this as an arithmetic progression and then figure out how to make it. It's not a trivial step.
Well, if you take your differences, no matter how far it goes, if you do 1 times x choose 0 plus, so your first difference times x choose 0 plus your second difference
Yes.
times x choose 1 plus your third difference times x choose 2.
That gives the quadratic progression. And you can keep going. I mean, I can have a cubic progression if I want to here. There's all kinds of ones. And I want to do one more that's important to us. That's the harmonic one. That is 1 over 1, 1 over 2, 1 over 3, up to 1 over k. I won't go into details of this right now. But what I want to do is now write all this in a more, so the summation part of them. So how do I do sums? Sums of a sequence, it's called a series. So this is sum from x equal 1 to 6 of ax plus b. That's how I write it, right? Because I already have an index for it, and I say that's effectively 4 plus 7 plus 10 plus 13 plus 16 plus the last one was 19. Right? If I want to write this one down, this is a sum for x equal 1 to 6 of, how do I write this? C r to the x, right? That is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 to the, if I have 6 things, that'll be 32. How do I write this one down here? This is a sum from x equal 1 to whatever value I want, ax squared plus bx plus c. And this here, it's a sum from x equal 1 to 1 over x. So how do I solve this series? Suppose somebody says, I want you to compute that. That is not figuring out what the next element is, but figure out the sum of a bunch of those. Or a sum of a bunch of those, or a sum of a bunch of those. How do I sum it up? So this is going to be, if I split it into two sums, let's say we go to n here. It's going to be a times the sum x equal 1 to n of x plus separately sum from x equal 1 to n of b. So a times this series has a value that you should know. X times x plus 1 by 2. N times n. Plus this, of course, here it's nb. So does everybody knows this? 1 plus 2 plus 3 plus n is n times n plus 1 by 2. Do we know this series? That's because I can write it n plus n minus 1 plus n minus 2 plus the last one is 1, right? That's the same. So that's s, that's also s. And now when I sum it up, I get how much is the sum here in each one of these columns. It's n plus 1 everywhere. And how many columns are there? So the total sum is n times n plus 1, but that summing as twice. Yes?
I can't read the top thing.
This?
Yeah.
Let me write again. Important for any arithmetic series is this sum here. This here, without the a, that is that value. So what we said is we have s equal 1 plus 2 plus 3 plus n minus 1 plus n. And the same s backwards is n plus n minus 1 plus n minus 2, right? Plus 2 plus 1. If I sum it up, I get 2s is n plus 1 plus n plus 1 plus n plus 1, right? Because each column sums to n plus 1. Therefore, s has to be n times n plus 1 divided by 2. How about in here? How do I do this? If I do this one, it's c goes in front, right? And then I get r plus r squared plus r to the n. Is there a formula for this I could use? How much is r? 1 plus r plus r squared plus f to the n. Everybody knows that formula? Is r to n plus 1 minus 1 divided by n minus 1. So this here, it's almost like that, but it doesn't have this 1 in the front, right? It's only this part. So it's c times this r n plus 1 minus 1 divided by n minus 1. But I have to take out that 1 that was extra. Because if I only write this result, I'm having what I need here, but here I don't have the 1 in the front. I would have a 1 if the sum would be from 0. If I have an x equals 0, r to the 0 would be the 1 in the front. So there are two steps here. How to do this summation, that's easy because this is a formula. But then the hard step is, who knows this formula? People have seen this formula before? Can you prove it? Well, let's multiply this little guy here with that, right? What do we do if we get r minus 1 times 1 plus r squared plus r to the n? Let's do the multiplications first with r. R times 1 is r. R times r is r squared. R times r squared is, what's the last one? R times rn. N plus 1, right? What's the next to last one? R at what power? So that is the r multiplying with 1 r squared all the way to rn. But now I have this minus 1. Okay. So how much is minus 1 times 1? Minus 1. Minus 1 times r. Minus 1 times r squared. Minus 1, what's the last one? Minus 1 times r to the n. How much is that?
Negative r to the n.
So what do we see here? R with minus r? 0. R squared with minus r squared? 0. This is going to be 0. This is going to be 0. So this all goes away. What's the end result? Minus 1 plus r n plus 1, which is right here. Okay? How many people follow this? Very good. So that's a geometric series. What about in here? This is 3 sums. It's a sum from x equal 1 to n of x squared. That's one chunk. Plus b sum of x equal 1 to n of x, which you already know how to compute. That's the sum over there. Plus, how many c's are in this sum? C is a constant, so how many c's are in here? N. There's n c's. So for this, we need a formula. The formula is n times n plus 1 times 2n plus 1 divided by 6. Not including the a, just this part. B, we already have a formula for this sum. It's n times n plus 1 by 2. And this is nc. Now this, we have no formula. Yes?
It's a little small. Can you read what you're multiplying by a again, please?
N plus 1, 2n plus 1, divided by 6.
Thank you.
This one, we don't have a formula, we have an approximation. This is like logarithm, natural logarithm. So logarithm base e of n plus 0.5772, I believe. That's a constant. So it's not an exact formula, it's an approximation that says this is like the logarithm plus a constant. So we have arithmetic progressions and their sums, geometric progressions and their sums, quadratic progressions and their sums, and harmonic progressions and their sums. So the principle that allows us to do all this easily, I mean, you can follow my high school, competency here in those formulas. And if you're lucky, you get it because you figure out how to do it. But that's not, there's a principle that will allow this to do all these sums and other things much more systematically. We don't have to be creative. What's that principle? It will allow us to prove these sums and a lot more. Nope. How can we prove these sums other than me starting being creative? Like I was creative here, I was creative here. Well, what if I want a system or systematic way to proving those sums? What would I do? Anybody knows how to do that? There's a whole principle like inclusion exclusion principle that allow us to do systematically all those things. induction will allow us to prove all this immediately. So induction is very simple. It's literally people in certain countries study induction before the first grade. Okay? So there's people who do inductions at kindergarten as a logical way of thinking. You know? It has to do with if I'm smart and I take a good grade in this course, that's the base case. And taking a grade in any course allows me to take a good grade in the next course. That means I'm going to take good grades all the way. If I start well, and there is a transition that says once you take this course and you do well, the next course you're also going to do well. That means you do well everywhere. So, principle of mathematical induction. There's a statement, Pn, for problem n. There is a base case that says P of 0 and P of 1, so forth, some of them are true. And there's the induction step that says if P of n is true, that's an implication, then P of n plus 1 is true. Or sometimes it says we need more than just P of n to prove that one. We're going to use P of n minus 1 and P of n, both of them are true. So there's two true things. That implies the next one is true. Like to do well in your next course, you have to do well in discrete and in fundis to do good in the next course, kind of thing. You know? So sometimes what you're doing now or tomorrow does not depend only on the previous thing, but depends on a bunch of things from the past. Right? And then that means, according to the induction principle, that P of n true for all n. Very simple thing that allows us to prove stuff little by little. So I want to prove this formula right here. This sum is this. So induction example 1. My P of n says the formula sum over x equal 1 to n from x squared, right? That was my sum here, is this value. N times n plus 1 times 2 n plus 1 divided by 6. I follow the recipe. Right? What's the base case? P0, P1. Let's start with 1. This is a statement for any n at least 1. What's the first, what's this, how does this look like for n equal 1? What is the sum here if n is 1? How many terms are in here if n is 1? Just 1, which is 1 squared, right? How is this? How much is this? If n is 1. So n equal 1. 1 times n plus 1 is 2. 2n plus 1 is
3.
Divide by 6.
1.
Is correct or not? Is 1 squared equal that? Good. So what's the induction step? Well, in induction step we know P of n is true. It's a premise. So we can use it. We already know that the sum from x equal 1 to n from x squared is 1 times n plus 1 times 2n plus 1 by 6. We have that already. Because in an induction step, we already assume P of n, the previous one, was true. Now we want to prove Pn plus 1. I'm going to write it here. Prove Pn plus 1. So for Pn plus 1, I need this sum of x equal 1 to n plus 1 of x squared, right? How much is that? That is the previous sum, x equal 1 to n of x squared, right? Plus the extra term. What's the extra term? So if you look at these sums, it sums all the squares. This is summing all the squares to n plus 1. But I say, how about you sum it first to n? What's the extra term that's not included here? So this is like 1 squared plus 2 squared plus 3 squared plus 4 squares all the way to n plus 1 squared. This in here is 1 squared plus 2 squared plus 3 squared all the way to n squared. What is the additional stuff that I need to add to make it correct?
N plus 1.
N plus 1 squared, right? The term that's missing in here, the last term, is for x equal n plus 1. That would be n plus 1 squared. Hands up with me here. Okay? So now I can use, I already know P of n, I know the sum. P of n is telling me how much is the sum. That is n times n plus 1 times 2n plus 1 divided by 6, to which I add the last term. So we want to prove Pn plus 1, right? Which says what? This sum from x equal 1 to n plus 1, so 1. 1 means it's not done yet. What is my expression here for Pn plus 1? How do I write this thing, but not for n plus 1 instead? What is n? N plus 1. What is n plus 1? That's n plus 2. What is 2n plus 1?
3.
That is 2n plus 1, right? Divide by 6. That's what I want to get. Let's see what I get here. I'm going to have an n plus 1 common factor in front of the sum. And then how much is left from this term if I take the n plus 1 out? N times 2n plus 1 by 6. And how much is left from the other term if I take an n plus 1 out in front of the sum? Let's do 6n plus 1 by 6. So now I sum up those two. That's n plus 1 times, this is 2n squared plus n plus 6n plus 6. Yeah? Everybody sees that? The n plus 1 here is this n plus 1. The 6 moved in front of the fraction. That's the 6. What I have here, where did I get 2n squared plus n? I open up the parentheses here, right? N times 2n, n times n. That's 2n squared plus n. And 6n plus 6 comes from 6n and the 6. Who follow me? I say this is n plus 1 by 6 times n plus 2 times 2n plus 3. N plus 1 by 6 is n plus 1 by 6, of course. What if I open parentheses? N times 2n is 2n squared. N times 3 a little error here.
Yeah, because you have n times 3 plus 2n times 2, which gives you
Right.
7n.
So I get 2n times 2, that's how many n's? 4. 3n times 3 times n is 3n. How many n's total in there?
7.
Which is 7n, right? n plus 6 is 2 times 3. Now, is this the answer I'm looking for here? N plus 1 by 6 is in front of the fraction. n plus 2 is n plus 2. And how much is 2 times n plus 1 plus 1? It's 2n plus 3, right? Right here. So that proves by induction this formula. Just a quick recap, how this stuff works. I prove the base case first, n equal 1. And then I say once you have it for any n, you have it for n plus 1. Therefore, it's got to be true for all n's. Like from 1 to 2, from 2 to 3, so on and so on. We can prove all this stuff by induction. Oh, there will be a recitation on Sunday. Conditionally to the regular one, there will be a recitation on Sunday. Can you turn off the camera, please? The red button on the right side.